Okay, hello class. Let's continue to the second part in this chapter. Okay, in this second part, we will move on the heat of the mixing. I will detail it later. Okay, these are the summary on the application of solution thermodynamics. Okay, previously we have learned about the fugacity to overcome the limitation of the chemical potential, which the fugacity is a mathematical manipulation expression. It can overcome the chemical potential, and we also cover the fugacity or activity coefficient in determine the expression related to the fugacity, and then from the fugacity versus mole fraction curve we can obtain the new concept of Lewis-Randall rule, which in ideal solution the species or the fugacity can be equal to its mole fraction. In this rule is equivalent to the Henry's law. It also has the equivalent to its mole fraction, but Henry's law is describing the composition for the low or the low concentration, and then Lewis-Randall rule describe the composition for the pure species. Okay, for the model of substrate energy, we covered the red Lewis. From the red list crystal, we have learned about the new equation on the Margulis and Van Laar. Okay, for the Margulis, the constant is 1, A1, 2, or A21. And for the Van Laar, it has A prime, 1, 2, and A prime, 2, 1. It's based on the GE equal over S1, S2, RT, and Van der Waals having the S1, S2 over GE, RT. So basically, this what we have covered previously. We also has been introduced to the local composition models such as Wilson and RTL, Uniquid, or they improvise on the unified. That basically is discussed on more on the interaction among the species. Okay, in this part, we will move to the heat of mixing with it equivalent to the enthalpy of mixing and excess enthalpy that give a heat of a solution. Okay, we will discuss about this, further discuss on this part. Okay, as a learning outcome, we will cover on the fundamental property relation, where you should be able to determine the heat effects due to the heat mixing process. Okay, for the heat mixing process, we will discuss on the enthalpy and also the mixing related to the volume. Okay, for the ideal gas can be served as a standard to which the real behavior can be compared in the gas state, or it describes the residual properties. And for the ideal solution also can be served as standard to which the real behavior can be compared, but we discuss it on the based on the solution, and it can be defined by the access property. The access property ME equal to the real minus the ideal solution. So this is what we covered previously. Okay, in this topic, we will use this concept of access property to relate it with the mixing or heat of mixing. Okay, as introduction to the property of the mixing. Okay, we have two different. Maybe I put as a vessel. Okay, the first content of we have a first component, or it also have initial of the chemical potential, and then we have second component, and the chemical potential for the second component is identified. Same goes to the third component. Okay, and then we have the mixing or mix of the components. So it turns to Ny plus N2 plus N3, and it has the another chemical potential. Okay, I denote as mu1, mu2, and mu3. Okay, for the free energy, or when we discuss it based on the Gibbs energy or the free energy, okay, before the mixing. So we have G, okay, I put as G1 equal to N1 mu1 plus N2, or potential, chemical potential for component put 2 initial at initial, and also the third component mu3. And then after the mixing, we will refer to this. This is after the mixing. So we have, maybe I put as G2 and 1 mu1 plus N2 mu2, and we have N3 mu3. So when we differentiate between the between after and before, so we have delta G mixing equal to, okay, this is equal to the summation of Ni mu I naught, and then we also can have this summation Ni mu I. So back to the delta G of the mixing is G2 minus G1. So G2 is this summation of mole composition, and the is chemical potential minus the Ni mu I initial as initial. Okay, we know that for the equation of the chemical potential, okay, mu I equal to mu I naught plus RT ln Si. So it gives us the equation or the expression for the chemical potential. This equation or describe for the mole fraction of this particular component. Mole fraction as particular component. Okay, and then when we replace this or the chemical composition, chemical potential, sorry, to this equation, it gives us the delta G mix for the, since it based on the mole, so molar equal to the change in the force energy over the total mole. So it gives us the RT summation of ln Xi over N. Okay, if the total mole is equal to 1, those delta gives a mix or be equal to the RT summation of ln Si. So this is the equation or to describe the delta G mix in the mixing. So how about if we describe it to another thermodynamic properties, such as the delta, for the delta entropy mix. Okay, this is the second, and this is our first expression. Okay, for the delta entropy, okay, we know that delta G equal to minus S dt plus V dP. Okay, for the entropy, we have dou G over dou T equal to minus S. So use this dou G to the delta mix. Okay, we have the delta S equal to dou over dou T, and we have delta G. Okay, for the mix, okay, that's mean we can, if the equation based on the mixture. So the delta S mix equal to, so you can replace the delta T, or we have the delta S mix minus or R T summation of log Si equal to the previous equation. So we have another expression to describe it based on the entropy. Okay, the third is the delta H, or enthalpy, change of the enthalpy in mix. So how can we use the existing expression to correlate it with the delta H? Okay, we know that delta H equal to delta G plus T delta S. We can insert the expression that we described previously into this equation. So delta G is the RT summation of S1 or Si plus T minus RT summation of Si. So we can cancel between these two. If you can see here, we have this. So equal to 0. So delta H is equal to 0. How about the volume? So how about to determine the change in the volume? So to relate it, we can use this equation. So we have delta G minus S dt plus V dP. So for the changes of the volume, so dou G over dou B equal to V. Okay, thus we can obtain the delta V equal to delta G over dou B. So based on the G we have been is, since it based on the constant pressure, so if we have this RT long summation of long composition, the delta V mix equal to 0, because when we based on the respect to the pressure, so it gives us the value of 0. So from this derivation, we can conclude that the change of the enthalpy and change of the volume equal to the 0. So what we're gonna do is to proceed the further heat of mixing between both property of enthalpy and the volume. So in conclusion, the property change of the mixing, or we have the ideal solution and excess property. Okay, to obtain the excess property, the real is minus the ideal solution. Same goes to the other properties. And volume and enthalpy gives us the property change of the mixing by using this general equation. And then finally, we can obtain the delta V and delta H in the mixing equal to 0. Okay, the delta V and the delta H, or the change of the volume and change of the enthalpy, equal to the property change of the mixing, or minus equal to the respective excess properties. Or it gives us excess volume or excess enthalpy equal to the volume of enthalpy change of the mixing. So that's what I explained to you previously in the previous slide, how we obtain the equation, or delta V equal to 0 as well as delta H. Okay, from this diagram, okay, it shows that all the system have different mixing properties but having the common characteristic. Okay, if we can see at the species, or for the pure species, example S1 equal to 0, or the pure species is component 2, or S1 equal to 1, S2 equal to 0. That's mean for the pure species, we can obtain the the delta M equal to 0 for all the properties. And then Gibbs energy change due to the mixing is always negative, or you can obtain the value of delta G is always positive, or we can relate from the previous equation, or we have learned SI. So if we, okay, because we know that SI should be between the 0 to 1. So if you insert any value along the S1, so it should be 1. So if we insert any value of composition within the 0 to 1, so it gives us the negative sign. So negative, that's why the delta G always negative. Okay, for the heat effect of mixing process, there are two types of heat effects due to the mixing process, which is heat of mixing or denoted by delta H, and we also have the heat of solution. Okay, heat of mixing or change of the enthalpy based on the 1 mole of solution. But for the heat of solution, it based on the 1 mole of solute. Okay, the heat of mixing or delta H is enthalpy change when pure species are mixed at temperature and pressure to form 1 mole of mass of the unit of the solution. So determination of enthalpy for binary solution from enthalpy data for pure species 1 and 2 and form heat of mixing. So this is how we determine the enthalpy based on the binary solution and also heat of mixing. So this is heat of mixing. Okay, the data for heat of mixing only available at certain temperature, which heat of mixing at other temperature can be determined similar to determine the heat of reaction. So you may refer to the reference table to determine the heat of reaction, because for the certain reaction, it has own specific value of heat of reaction. And then the heat, the energy change during the mixing due to the interaction between the molecular forces known as heat of mixing. Heat of mixing is less than energy change due to the breaking of chemical bond. Okay, the breaking of chemical bond known as the heat of reaction. Okay, for the first is for the first heat or heat effect is heat of solution. Okay, when the solid of gases dissolve in the liquid, okay, we call as heat of solution, that it based on the dissolution of 1 mole solute. That means solute, the interaction of the solute and solvent give us the solution. If species 1 is solute, or we have S1, is a mole of the solute per solution, because delta H, or the heat effect per mole of solution or heat of mixing, or we can have delta H over its mole, so it gives us the heat of solution. The mixing process can normally be represented similar to any reaction equation. For example, if we mix 1 mole of lithium chloride in the solid form, we dissolve into water, so we can get the solution. Formula of lithium chloride or 12 mole of water represent a solution of 1 mole of lithium chloride dissolved in 12 mole of equation of dissolved in 12 mole of water. Okay, this schematic diagram shows the mechanism in producing the solution. Okay, first we have the solute and also the solvent. Okay, the first step is to disrupt the interaction between solute and solute. Okay, this is to disrupt the interaction between solute and interaction between solvent. And then the next step is we can form or produce the solution once the interaction between both a solute and solvent, solid and solvent have been described. Okay, the enthalpy also relate to the endothermy and exothermy. Okay, if you can see from the figure A, yeah, we can see that this the delta H or the delta H, which is the start trip to perform the solution, has higher than the submission of the delta H2 and delta 1. It gives the exothermic solution. That's mean heat is released from this process. And for the endothermic solution formation, so the delta H is much less or smaller than the submission of delta H2 and delta H1. Okay, the difference of the type of heat is depending on the nature of the solute. It gives whether exothermic or endothermic. Okay, another example to relate it to the real application. Example, we have the instant hot pack and cool pack. Okay, in general, the calcium chloride in solid, or you can imagine in this instant pack, or it has the calcium or the mole of the calcium chloride and 1 mole of calcium. It has 1 mole of calcium and 1 mole of the chloride plus the heat to be inserted into the solution. So the enthalpy change also occurs when the solute undergoes the physical process of dissolving into the solvent. So we can obtain the heat of solution equal to minus 82 from so we can obtain the heat of solution equal to minus 82.8 kilojoule per mole. So the heat of solution is described based on the change of the heat into 1 mole. Okay, let's take a look on the simple example for you to have a deeper understanding on the heat of solution. Okay, the molar heat of solution of sodium hydroxide is minus 445.1 kilojoule per mole. In an experiment, 5 grams of, okay, this is the mass of sodium hydroxide is completely dissolved in 1 liter of 20 degrees Celsius water in form of calorimeter. So 20 degrees Celsius is initial temperature. As you may know, heat loss calculate the final temperature. What is the final temperature? So the first is to extract all the information. So we know that the delta or the heat of solution equal to the change of enthalpy in 1 mole. So to determine the delta or to determine the final temperature, we can use the equation of delta H equal to mCp delta T. Okay, M is represent the mass of this total mass. That means the solute and also the solvent. How can we determine the total mass? That means we mc equal to m solute plus m liquid or the solvent. Second is to extract all the information or list out the additional information that gonna have in this solving the problem. So we have this delta H equal to minus 440.1 kilojoule per mole, and then the mass of solute is 5 grams. And then we have mass solvent in, we don't have mass solvent, but we have the volume of solvent is 1 liter. So we need to determine the mass of solvent. And then we require a molecular weight since we need to cancel the mole unit here. So we have 40 gram per mole. This is molecular weight of sodium hydroxide. So we can, the third is to solve this equation. So to cancel the unit of gram, so we need to consider the molecular weight. So from 5 gram of sodium hydroxide, so insert into 41 kg mole. So we can have the unit of mole, sodium hydroxide. So what we can determine is delta H. So in 1 mole, so we have the heat of solution is minus 445.1 kilojoule. So the unit, or maybe we can use joule if you like to use a joule. So 1 kilojoule equal to 1000 joule. So we can get the answer is minus 5.56 times 4 joule. Okay, next is to determine the mass of solvent. Okay, to determine the mass of solvent, we can assume as the mass is equal to 1 kg by assume that density is 1 kg per liter. Okay, and then the last step is to insert all the known parameters to obtain the final temperature. So we have delta T equal to delta H over mCp. So the delta H is minus 5.56 joule. So we have M is, since this is 1 kg, you can convert into 1000 grams. So 1005 grams. And Cp is, this is the standard value of Cp is 4.18 joule per degree Celsius. And then you can obtain the value is 30 or delta T equal to 13.2 degrees Celsius. And then Tf is equal to 33.2 degrees Celsius. So this is the answer. Okay, in conclusion, that we can obtain the enthalpy or change of the enthalpy from the heat of solution. Okay, since from this example, the heat of solution is given. How about if in the problem, the heat of solution is not given to us? The other way to determine the heat of solution from the standard heat of formation, or you may refer to the appendix 4 or appendix 6 table C.4. Okay, the following data are the example of heat of formation for of 1 mole of lithium chloride. So the first example, we have lithium chloride in solid or as solid, or if we have 1 mole or dissolved in 1 mole of solvent or water. And this is for the second mole, third mole, and so on. Okay, heat of formation can be interpolated in usual manner to obtain the intermediate heat of solution. Example, we need to define the lithium chloride in 7 mole of water. So how can we obtain it? You may refer to this. We only have 5, 8, but we don't have the 7. So to obtain the lithium fluoride in 7 mole of water, we can perform the interpolation. So from this information, we can interpolate between 8 and 5. So you can interpolate it to obtain the value of heat of formation for lithium chloride in 7 mole of water, and this is the answer. Okay, what is the difference between heat of solution and heat of formation? Okay, we already defined the heat of solution. With to perform the heat of solution, it required the interaction between the solid and solvent. Okay, for the heat of formation, It based on the standard heat of reaction for the formation of 1 mole of the species from each element in their naturally occurring state. So the heat of formation or denoted by delta HF or based on the element plus element or give the compound. Example for the lithium chloride. So that's mean we have lithium as the element plus the chloride to give the heat of formation for lithium chloride. Same goes to determine the heat of formation of lithium chloride in 3 mole. So we can, the elements are lithium chloride, 3 mole of hydrogen and 3/2 mole of oxygen. So we can obtain this. Okay, there are 2 ways to determine the heat of solution. Example, to determine or to obtain the heat of solution for lithium chloride in 5 mole of solvent. We can perform the balance to determine the heat of solution. Example, first we have the heat of formation for the lithium plus 5 mole of water. So this is the value you can obtain from the reference table. And then second, we need to cancel this part or lithium plus a chloride. So we can also have the heat of formation for the lithium chloride only. So by cancel it, we can the lithium chloride plus 5 mole of water give us the heat of solution. So using this balance or summation of all the heat of formation to give the value of heat of solution. Okay, the other way is from the calculation part. Okay, example, these are the required reaction to produce the lithium chloride in 5 mole of water. So the first part is from the lithium chloride of 5 mole in 5 mole of water, we can produce this heat of formation. And then second, from this heat of formation, we can plus all the elements to give us the heat of formation for lithium chloride. And then finally, that we can obtain the heat of solution. So plus the first step and second step to give this the final answer. Okay, let's take a look on the next example. Based on the following data, determine the heat of solution for the A, 1 mole of sodium carbonate in 50 mole of water. So what is the heat of solution for 1 mole of sodium carbonate in 50 mole of water? So we need to, based on the heat of formation, so to produce the solution, that means we have this solute and also the solvent. Okay, the solute is we can use this, the value or the solute, and then the second is solvent. Solute in solvent is natrium carbonate in 50 mole of water. Okay, the next is to produce 1 mole of sodium carbonate monohydrate in 15 mole of water to form 15 mole of water per mole of sodium carbonate. Let's take a look on the A first. Okay, for the A, to produce the 1 mole of sodium carbonate in 50 mole of water, so we can use the calculation part. Okay, the first part is to determine the heat of formation or to consider the heat of formation for the solute first. And then second, to include the 50 mole of water, and then you can determine the heat of solution for this. Or we can use another method based on the relevant reaction. So in producing the sodium carbonate in 50 mole of water, so it based on the element of sodium, carbon, oxygen and water. The heat of formation are given. And then second, we can cancel this part to obtain the heat of formation for the solute only. So the given value, if we have 2 nitrogen plus carbon 3O2 oxygen equal to minus 270.3. But since we need to cancel this element, so we can have, instead of having negative, so we can have the value is positive. So plus between the first reaction to the second reaction, we can obtain the heat of solution. Let's take a look on the next solution. So we have sodium carbonate in 14 mole of water to obtain the sodium carbonate monohydrate in 50 mole of water. So based on the calculation part, the first part is for the solute. So we have this, you need to produce all the element from this part. So we have the sodium, carbon, oxygen, hydrogen, as well as the oxygen. So and then we need to plus with for 15 mole of water. And then from this we can have this is for the part of water, and then plus 40 mole, it gives us the 50 mole of water. We sum up all the value, so we can obtain the heat of solution using the calculation part. Okay, for the second method based on the relevant reaction, so first we need to extract all the information from sodium chloride, water plus 40 mole of water. So we have sodium chloride, carbon, oxygen, water, and 14 mole of water. So it gives us the 14 or sodium chloride, chloride monohydrate in 15 mole of water. Okay, from this we can to cancel out the H2O first. So H2 plus O2 plus O2, we can have this H2O. So you may cancel the H2O. Okay, the first cancel H2O, and then second one as we need to cancel is the term for the element for the solute, right? So we can cancel this part 1, 2, 3 from this using this, or we need to determine the formation of sodium chloride in 1 mole of water. And then after that, once we cancel this part, so we can obtain the sodium chloride in water plus water plus the 14 mole of water, it gives a 50 mole of water. So you can insert this, or if for the formation, that's mean element plus element equal to compound. So if you have this value, that's mean we disrupt this interaction or the solute interaction. So we have the positive sign for this reaction. So and then sum up everything, or the sum of all the formation, the heat of formation, and then you can obtain the value of heat of solution. Okay, how about to obtain the value of heat of mixing, or the mixing heat from the graph of heat of solution versus the mole. Usually mole is based on the solvent or water per mole of solute. So let's take a look on the expression or elaborate here. So for the mole in the solution is based on the mole of species 2, or example, if the mole of solution, or the solution considered for the component 1, so the mole of solute can be determined based on the mole composition for component 2 over component 1, or equivalent to its composition for component 2 times the total mole. Or if we have the mole of the component 1 can be determined from the composition times the total mole. Or we can rearrange to have 1 minus S1 over S1. Or the composition of the S1 equal to 1 over 1 plus the mole or the mole of the solution. And then to relate it with the heat of solution, we know that heat of solution is equal to the heat of the mixing over its composition, or we can replace it to the mole of the solute. So this is how we can obtain the value of heat of formation by referring to this diagram of heat of solution over mole of the, which is a mole of the water per mole of solute. Or in simple way, we can define it as a mole of solvent per mole of solute. Okay, the enthalpy composition diagram represents the enthalpy data for binary solution. It consists of the plotting of enthalpy as function of the composition. Okay, the composition can be at the mole fraction or mass fraction for one species with the temperature as parameter at constant pressure. Okay, pressure usually we use the pressure at 1 atm. Okay, the enthalpy is based on 1 mole or the unit mass of the solution, or the enthalpy equal to the composition of binary solution plus the heat of mixing. Okay, since there is no absolute value or arbitrary 0 point are chosen for the enthalpy of pure species, that means H1 equal to 0 at certain condition for species 1 and H2 equal to 0 for the species 2. Another information that we can obtain from this diagram or enthalpy versus the composition is the adiabatic mixing. All the solution formed by the adiabatic mixing with for two other solution are represented by points lying on the straight line. So we can example, maybe I can show to you later. So we have enthalpy and the composition. So maybe the data is like this. So to obtain the point by considering it adiabatic, so we can draw a straight line lying to this to obtain the value for this point. Example of HS diagram for the sulfuric acid. So we have enthalpy versus its composition based on the mass fraction. Okay, if we draw a straight line, so this is the line for enthalpy equal to 0. So for this point, we can see that this is for the H2 equal to 0. H2 equal to 0, that means, okay, if we have the for the sulfuric acid, okay, example S1 is referred or described for the sulfuric acid, and then the fraction or the S2 another or sulfuric acid in water. So if S1 equal to 0, that means S2 equal to 1. So for the pure species of water, S2 will be equal to 0. And for this point, S1 equal to 0, that means if we have S1 equal to 1, referring to the sulfuric acid, and then S2 equal to 0 is referring to the solvent of water. So we have S1 or enthalpy equal to 0. Okay, adiabatic mixing, if we have the underlying point or the line or the straight line between 2 points for the solution of A and B. It gives the point here known as for the adiabatic mixing. Okay, this diagram is to summarize or the detailed explanation on the enthalpy versus composition. Okay, you may recall from the explanation on the graphic relate to the partial properties. Okay, we have for the pure species 2, we gonna have this the value of this partial properties of component 2, and also this is for the pure species. And same goes to the pure species 1. Okay, the straight line is represent the ideal, the line for the ideal solution, which connected for the enthalpy of pure species 2 and 1. So we can have this ideal solution. Okay, if we have the line is below the ideal solution, that means the delta enthalpy or the mixing enthalpy is equal to the negative sign. Okay, or if based on the knowledge on the enthalpy, if we have the negative, that means we have this exothermic. So we call as exothermic. Or if it has the opposite line, that means we have the positive value of higher than the ideal line. So we have the positive value is endothermic. Endothermic, that means heat is absorbed into the system. Okay, the tangent line to determine the partial enthalpy. We can obtain the partial enthalpy by draw a tangent line from the actual line or the actual data of enthalpy for the component 1 and 2. Okay, thus the delta enthalpy or represented by the real minus the ideal solution of the enthalpy. It gives us the excess energy or the heat of enthalpy of the mixing equal to excess energy. Okay, let's take a look on the example 4. Okay, for related to the adiabatic, of how can we use the diagram in determining the heat of mixing. An aqueous solution or sodium hydroxide about 10% at 21 degrees Celsius is made with another aqueous solution at 70% of sodium hydroxide at 93 degrees Celsius to form a solution that contains 40% of sodium hydroxide. Okay, A, if the mixing process is done adiabatically, what is the final temperature for the resulting solution? So you may refer to this diagram. Okay, we have 10% and 70%. So we have 10% and 70%. So you may draw a straight line at what is the temperature? Is okay, the 10% is 20. Okay, 10% is at 21st degree Celsius. So this is the point. And then for the 70% is at 93 degrees Celsius. So maybe this is the line. So we can draw a straight line. So at 40 degrees Celsius, so you may refer to this, we can obtain the temperature, which gives us the value of enthalpy as well the temperature. Okay, the next is the final temperature in part A is reduced to 21 degrees Celsius, how much heat must be removed during the process? So we can get the temperature. So it removes to 21st degree Celsius. So this is the by remove the heat to this temperature. So what is the value of how much heat must be removed? So how much heat must be removed is, okay, we have, okay, first we have 447, and then second to draw to this line, and then you can refer to this straight line, or you may drag to obtain the value of enthalpy. So it gives the 163 joule per kg. Or in detail explanation, okay, so this is the second at 21st degree Celsius, and this is at initial we obtain from the by draw a draw a connecting line from the 21st at 10%, and also the 93 degrees Celsius at 70%. So we call as adiabatic. And then to obtain the delta H, so we need to minus the value that we obtain at 163 kilojoule per kg minus 447 at this point or adiabatic that we obtain, it gives the value of enthalpy, or what is the heat required is minus 284 kilojoule per kg, or this value is the involved of each kg of solution form. Okay, I think this is the last part. Okay, so for the next topic is moving to the next chapter is related to the chemical reaction equilibrium. Okay, in summary, we have learned about the heat of mixing, which from the heat of mixing we can obtain the heat of solution. Okay, the heat of the solution can be determined from the heat of formation, whether you use the based on the relevant reaction or you use the calculational part. And then for the last part, we also cover in determining the heat of mixing from the graph of heat of solution versus the composition. And from that, the enthalpy versus composition diagram, we also have learned about the determining of the heat of solution in adiabatically or in adiabatic mixture with by producing connection between the one mixture to another mixture. Okay, by end of this part or this slide, I ended my my lecture today, and until we meet for the next chapter. Thank you for your attention. Bye.